In Lab 4 Circuits and Capacitors for the course of Physics 2 2012. In this lab, we predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of unconventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. When we're using Ohm's law, capacitance, the conservation of energy, also known as Kirchhoff's loop rule, and the conservation of charge, Node rule. The procedure is using the online circuit construction kit in order to simulate the circuit below. So for this experiment, we use the ammeters, which show the same reading even if they're reversed or not. This reading is 0.02 ampere. So we also see the voltmeter being used. The red cable or the black cable used in the specific spots can show either a positive or a negative value. The voltmeter has great resistance and therefore opening the circuit, so the ammeter shows 0. The voltmeter shows the voltage of the two batteries, which is 3 volts. So here we add up the potential differences of the circuit, and we see that we can use either measure its battery or both of them. So 2 times 1.5 or 3 volt, and by adding them up, here we can see that 3 volt minus 0.959 minus 2.041 from the two resistors, we get 0 volt, which is exactly what we want since we know Kirchhoff's loop rule. We see here the graph of potential versus position around the circuit, seeing that the slope of the graph is steep where the electric field is charged. And we have some observations that when connecting the voltmeter across 100 resistor, the ammeter reading is the same. When we attach the voltmeter, we alter the circuit, but the ammeter reading doesn't change because the voltmeter is connected parallel to the circuit. It has great resistance, and therefore the current doesn't pass through the voltmeter, and ammeter reading remains the same. And even we replace the voltmeter with an ammeter in parallel with the 100 resistor, the same thing happens for the same exact reasons, and we see the picture on the right. We also have the calculations of resistance V over I for its resistor, and we get also that the resistance of wire and the ammeter is 0, since we are doing ideal. This is our lab's ideal, and we get the red numbers from the observations of the CSK and the blue numbers from the readings of the ammeter. We also handle capacitors, and we see here that the voltage of the capacitor increases as it's being charged, and the delta V decreases, and therefore the current decreases as well. The current always decreases from Imax to 0. And then we also see that when the voltage of the capacitor decreases and it becomes discharged, the current also decreases, and here the capacitor acts as a battery, and therefore the current always decreases from Imax to 0. We also make measurements measuring the time it takes for the two different resistors to be charged and discharged, and we see that, of course, the time it takes for the specific resistor to charge and discharge is almost the same, but we see almost a double increase of the time being charged and discharged of the 20 resistor to comparing to the 10 resistor. We also use a 9-volt battery, the capacitor, 200 millifarad, and 30 ohm light bulb in order to measure the voltage across the capacitor with a voltmeter, and use a stopwatch, creating data of voltage versus time. And we see here more specifically this data, and we make calculations using ln, delta V versus delta VO. Delta VO is the fixed 9-volt value, and we use the formulas below, and that the fact that the slope equals -1 over RC, and we get that the RC is 6.07 seconds, and that's how we find the time constant. So here we have the measured time constant, which is kind of has a slight difference from the expected one, and which is of course human errors using stopwatch. And we see also that the graph is not exactly aligned, and this is also like another indication that we made a few human errors using the stopwatch. So what if we were doing the lab in real life and using an actual ammeter? What would be the differences? The difference is that the ammeter would have resistance, and therefore we have reduced accurate values. So our numbers would be different. They will have reduced. And if we're doing the lab in real life and use the real battery to charge the capacitor, the model would be pretty different, because in real life the real models would have resistance, slowing down the process of the capacitor charging, and therefore it would take more time to charge. In contrast with an ideal project where they will be instantly charged and discharged. Thank you very much for your attention.